everyone, welcome back to the graph series. In this session, we are going to solve and code the problem of is there any path that exists from any one vertex u to v. Okay, so here you can see this is the given problem. Find if path exists in graph. Problem number 1971, leetcode.com. There is a bidirectional graph with n vertices where each vertex is labeled from 0 to n minus 1. So the vertices are labeled from 0 to n minus 1. Inclusive of both 0 and n minus 1. The edges in the graph are represented as a 2D integer array edges, right? So you have been given a 2D array which is going to store all the data about the edges. It is kind of an edge list kind of an representation where you are given a list of edges, okay? Where each edge I is represented from ui to vi, any vertex ui to any other vertex vi. And it denotes a bidirectional edge between ui and vi, so we know that it's an undirected graph, where every vertex pair is connected by at most one edge and no vertex has an edge to itself, right? So there is no self loop, right? You want to determine if there is a valid path that exists from the vertex start to the vertex end. Given edges and the integers n, start, end, return true if there is a valid path from the given vertex start to the other vertex end. Otherwise, you can return a false. For example, let's say this is the given graph and you are given start as 0 and end as 2. So here you can see there is a path from 0 to 2. So the answer should be true. Whereas here, if this is a path, so this is a graph. So see, this is not a connected graph. It's a disconnected graph. So if from 0 to 5, someone asks you to check if there is a path from 0 to 5, so there is no path. So you are going to return a false. Okay. Looking at the constraints, you can see n can be as big as 10 raised to the power 5. The length of the edges can be as big as 2 into 10 raised to the power 5. That is the number of edges will be 2 into 10 raised to the power 5. Right, and rest of the constraints are like simples. There are no self edges, there are no duplicate edges. Okay, you can see if you want to check if which companies have asked this. So Microsoft 2 times in the last few part, and these are the related topics. Okay, so this is the corresponding question. Okay, now what we are going to do, we can copy this code snippet, right? So this is the function, I would say, signature that is present here, and I can come to my Sublime text. I am pretty much comfortable here coding it. So let's say I have to implement this function, right? This function is something that I have to implement. Okay, cool. One thing that I would like to add is std, because you know I don't using namespace std. That's not the best practice to always go for. And this is the corresponding signature. Okay, cool. Now let me show you what we discussed in the theory part, right? In the theory part, we wrote this function, right? So we are going to implement the function as it is. You can assume that this f is the function, has path. So I'll write a function bool has path, okay? And then it will take a graph. So we are going to take an adjacency list based representation. So std list of integer and graph. It is going to take a start and it is going to take an end, right? So these are the things that it is going to take. And apart from that, we also need the visited. We need a Boolean visited vector. So it will be of bool and visited. And if you will carefully see, I'm passing all the vectors by reference, because otherwise it will start creating copies. Okay. Now, if let's say what I said here, you are going to go to all the neighbors and check if any of the neighbors is going to have a path, you are going to return true. That's why we have done an OR operation. So what you can do is for auto and neighbors in. How can we get the neighbors? We can traverse the linked list at graph at start, right? We are going to traverse all the neighbors. If the neighbors have not been already visited, because you know that in an undirected graph, the neighbor will be having again your reference as well. So you are just going to see if not visited at neighbor. If the neighbor is not visited, then we are going to visit it. So you can say bool result is equals to has path. Graph will be passed as it is. Now, instead of finding a path from start to end, we are going to find the path from neighbor to end. So neighbor, this is neighbor to end and visited as it is. If you have found a path, here you can see if you have found a path, then we will check if result If we have found a path from the neighbor to the end, then definitely we have found a path from the source to the end as well. So I'll return a true from here. If you are not able to find a path from any of the neighbors, like when this loop is going to exit, this loop will exit when you have successfully traversed all the neighbors and you are sure that from none of the neighbors there is a path from that neighbor to the end. If there is no path from any neighbor to the end, we are going to return a false. See, as simple as that. So we just went to all the neighbors. See, we went to all the neighbors, and instead of just like doing an OR operation, we just put an if check. You can also like have a result, or for every iteration you can OR all the results, and you can like return the result corresponding to that. Okay, time for a base case. Time for a base case. If start is double equal to end, that is always a true, because you always like from end to end you can always obviously go. And before moving to any of the neighbors from this start, we need to mark this start visited, because otherwise these neighbors are going to recursively call back to the start. So visited of start equals to true, and that's it. This is the whole, I would say, DFS implementation. Now let's just make a graph here. Now I've already told you how you can quickly make graphs, right? So we are going to make a graph, std vector of std list of int graph. How many vertices we have? N vertices. Every vertex is going to have a list of integers, and that's it. And then you can traverse all the edges. So for auto and edge in edges, right, you can have u is equals to edge of 0, you can have v is equals to edge of 1, and then you can do graph dot pushback u, and let's say this is graph of v dot pushback u and graph of u dot pushback v. Why? Because it's a undirected graph. It's an undirected graph. So we have created the graph here. Now we will create the boolean visited vector. So bool visited, and the size should be n and initialized by all false, right? So the whole vector will be initialized by false, and then you can do return has path from graph, and then start can be passed as it is, end can be passed as it is, and then you are going to pass visited. Okay, so let me copy all of this code. And let me paste it here. Okay, so this is the code. Let's just try to do a sample test case run. Okay, things are working fine. Let's just try to submit it. See, works perfectly fine, right? Okay, now we need to see what is the time complexity of this implementation as well as the space complexity. So I would like to take a screenshot here of the code that we have written. I'll take this much screenshot probably, and let's just try to transfer it to the iPad. Okay, now let's just do the analysis. So this is the code that we have written. Okay, cool. Now if you will carefully analyze, this whole code is a recursive code. It's a recursive code, right? So obviously the call stack is involved. So we'll see what's the call stack. But on an average, what you can see is when you call this function has path, this function is going to traverse each vertex once. So you're going to go to a vertex and then go to all of the neighbors. So each vertex is at max touched once. You are not going to traverse the whole thing for the vertex again and again. Why? Because you are marking the vertex visited here. So you're not going to traverse it again and again. So you're going to go to all the vertices one. Okay. And then this loop, for each vertex, it is going to all the neighbors. That means it is going to go to all the edges, right? So you are going to traverse each edge twice, at max twice, one from one edge, one other iteration from the other edge. So if you will do a big O analysis, then the time complexity of this code will be big O of V plus E. Why V plus E? You are going to touch all the vertices once at max, right? because if it is a connected graph, then you are going to touch all the vertices once. If it is an disconnected graph like this, right, then you are not going to touch all the vertices. You are going to just touch some vertices that are connected directly to the directly or indirectly to the start node. Okay, so at max you can touch all the v vertices, and at max you can touch all the edges. So you can go here, you can go here, and that's it, right? So at max you can touch all the edges. So this time complexity is going to be v plus e. Now talking about the space complexity, so you can see the space complexity from some graphs like this. So what will happen is, in the worst case, the space complexity can be, you go here, then you go here, then you go here, then you go here, right? So if you have a linear kind of a representation of a graph, a graph like this, which is exactly like a path only, this will be the worst case. In this kind of a case, how much space you are going to take? The maximum space that you are going to take will be equal to the number of edges, right? Otherwise you will be having some lesser edges only, not anything more than that, right? So the space complexity is going to be something of order of edges. So this is the time and space complexity analysis for the hash path problem. Now using this, you can see the time and space complexity analysis for DFS also, because it is the exact representation of DFS that you can write, right? Okay. Sometimes in order to travel the whole graph, if let's say this is a disconnected graph, sometimes people, what they do is traverse one component separately, then traverse rest of the components separately. So instead of calling hash path from only the start, some people also put a for loop, and then all those vertices which are not yet visited, they call the hash path from those vertices. So let's say you call the hash path from this vertex, you will travel this component. Then you will call hash path from this vertex, it is already visited. You will call hash path from this vertex, it is already visited. And then you call hash path from this vertex. Now in that case, this whole component will be traveled. Now you call hash path from this vertex, it is already traveled. Hash path from this vertex, it is already traveled. So in this manner, you are able to touch each of the vertex one. But in order to do that, you have to replace it with a for loop. But the overall complexity still remains same. That is maximum the number of vertices plus the number of edges. Right. So I hope the analysis and the coding solution for the hash path problem is clear to you all. You will find the problem link in the description section. So please do check it out. And if you have any doubt, so don't forget to drop your doubts in the comment section. And if you like the video, don't forget to hit the like button. Don't forget to subscribe to the channel and hit that bell icon so that you can get a notification whenever we are going to put a new video on the channel. So that being said, we'll see you in the next session. Till then, take care guys. Bye-bye and love you all.